Let's take a look at example 4. I want to use the first derivative test to determine whether each critical point that we can find is a relative maximum, relative minimum, or neither. I'm going to take these two rational functions, 1 over x squared and 1 over x. We are going to use the same techniques we did before. 1 over x squared is equal to x to the minus 2 power. Let's take a derivative of that. R prime of x is equal to negative 2 x to the negative third. That can be rewritten as negative 2 divided by x to the third. If I'm looking for critical points, this fraction can never be 0 because we have no way of getting 0 in the numerator. But this fraction could have a situation where the first derivative does not exist. The first derivative does not exist when the denominator is equal to 0. That means x to the third would be equal to 0. The only way x to the third could be equal to 0 is when x is equal to 0. So we get a critical value when x is equal to 0. If I'm looking for increasing and decreasing, we could break up the real number line at that critical value. So we could create an interval from negative infinity up to 0. And then we could take the interval from 0 to positive infinity. We can check on each of these intervals whether or not our function is increasing or decreasing. Let's pick out a number from negative infinity up to 0 and plug it in to my first derivative. I'm going to choose the number negative 1. If I choose the number negative 1, I get a function output, which is negative 2 divided by negative 1 to the third power. And when you calculate that, you get a 2. So I know from negative infinity up to 0, r of x is increasing. If I look at the other interval, that is the interval from 0 to positive infinity, I can do a similar thing. Let's plug in x value of 1. When you do that, your output will be negative 2 over positive 1 cubed. That's a negative 2. So the r of x is decreasing on the interval from 0 to infinity. Now, we may say, well, r of x is increasing, and then r of x is decreasing. And if we're not careful, we could end up saying, or at least we could end up thinking, that going from increasing to decreasing must look like this and give me a maximum. It turns out we don't have a maximum value at x equals 0. The reason we don't have a maximum value at x equals 0 is because if you look at this r of x, we actually end up with an asymptote at x equals 0. The fact that this was a critical value was great, but we got the critical value because the r prime did not exist. If you remember, the maximum and minimum values have to occur on intervals where our function is differentiable. So this was a little bit of a trick. We have a critical value at x equals 0, but the function is not differentiable when x equals 0. And that means actually this first derivative test does not work when x is 0. If we're not differentiable, then the first derivative test does not work. So be careful about that. A lot of times people will say, oh, we're increasing on one side, we're decreasing on the other, therefore it must be a maximum. But in this case, it's not a maximum because that's where we get an asymptote. And so the limit as x goes to 0 is infinity of the function r of x. So the limit as x goes to 0 of r of x is infinity. And therefore, we actually don't have a maximum or a minimum for this r of x function. So be careful about that. The first derivative test does not work when the function is not differentiable. In this case, we have an asymptote at x equals 0. That's not the case for every single non-differentiable function, but that's the case for this one. You can imagine what's going to happen here. With p of x equals x to the negative 1 power, we can take a derivative. P prime of x is equal to negative 1 x to the minus 2 power, or said differently, negative 1 over x squared. We can see again, we have one critical value, and that is at x equals 0, and the critical value produces a derivative which does not exist. So it's not differentiable. The first derivative test would not work here. This p of x equals 1 over x does also have an asymptote at x equals 0. So we do have a critical value, but it produces an asymptote, just like previously our critical value produced an asymptote. Now, all of this stuff is still true. Don't forget, r of x is still increasing from negative infinity up to 0, and r of x is still decreasing from 0 to infinity. We could do the same thing down here. The first derivative test doesn't work, but we can still say that from negative infinity up to 0, let's check out if this increases or decreases. Let's plug in a -1. We would get an output of -1 over -1 quantity squared, which is -1. So my function p of x is decreasing from negative infinity up to 0. From 0 up to positive infinity, we can find whether we're decreasing or increasing there by plugging in a positive number. I'll plug in a +1. The output is -1 over +1 quantity squared, which is -1 again. And therefore, my function is also decreasing along the interval from 0 to infinity. Now, decreasing to decreasing, obviously that would not have been a first derivative test anyways. We know we can't do the first derivative test because at 0, because we're not differentiable there. I did want to show you the graphs of these two functions to see what's going on and why we don't get a maximum or a minimum at those two places. I have graphed the function r of x equals 1 over x squared here. Notice at 0, both sides are shooting up towards infinity. So as x approaches 0, y approaches infinity. We get an asymptote there, but there's actually no maximum. Because the limit goes off to infinity, there's no maximum possible. So it kind of looks like we should have a maximum, but we never actually connect because it shoots off to infinity. When you graph p of x equals 1 over x, let's just do y equals 1 over x. You get a function that looks like this. And you can see as you approach 0, one side shoots down to negative infinity, the other side shoots up to positive infinity. And so there's no maximum nor minimum. So the asymptotes of these functions produce non-different points at which the derivative doesn't exist. So the first derivative test doesn't work well when we have asymptotes. We have dealt with the absolute value function a few times. In example 5, it says use the first derivative test to determine whether each critical point is a relative maximum, a relative minimum, or neither. And now we have the absolute value function. Let's start that process. We have seen before that the absolute value function can be thought of as a piecewise function, where if you plug in a positive number, it gives you back that number. So you get an x if you plug in a non-negative, so for x greater than or equal to 0. And if you plug in a negative number, you get the opposite of that number. So you get negative x for x less than 0. I believe we've taken the derivative of this piecewise function before. Hopefully you remember that. The derivative, well, the derivative when x is greater than 0 is just going to be the derivative of x. So you're going to get 1 if x is greater than 0, because the derivative of x is 1. When x is less than 0, we're going to get a derivative that's -1. And we have a sharp corner when x is 0. So the derivative does not exist when x is 0. Let's write that down. So we get a derivative, which is 1 for any x, which is greater than 0. We get a derivative, which is -1 for any x, which is less than 0. And we get a derivative that does not exist if x is equal to 0. Now, the only time the derivative could be 0 or not exist is if x is equal to 0. And so in this case, we have a critical value of x equals 0, because that's the only place where absolute value does not have a derivative. Now, technically, the first derivative test should not be used. But knowing the fact that this is a sharp corner and knowing the fact that this is a continuous function, I can still think from -infinity up to 0. Well, from -infinity up to 0, the derivative a prime of any number, let's take a prime of -2, is equal to -1. Any number where x is less than 0, derivative is negative. So we know that our function is decreasing Let me rephrase that. The function a of x is decreasing from -infinity up to 0. We can also see that if I take the interval from 0 to +infinity, the derivative, let's plug in a number which is positive, let's say 10. Well, if I plug in the number 10, I got to plug it in, since it's greater than 0, I got to plug it in here. I get an output of 1. Therefore, my function a of x is increasing along the interval from 0 to infinity. Since I know it's continuous, and since I know the reason why the critical value doesn't exist is because we have a sharp corner, I kind of know that my function is going to look like this, and I kind of know this point is going to give me a relative minimum. So sometimes the first derivative test shouldn't be used, but still I can logically think through why I get a relative minimum here. Other times, the first derivative test can't be used, and you end up with things like asymptotes like we had in our last example. So it kind of depends on the situation. But again, the first derivative test should not be used when our function is not differentiable at a point. We have to be really careful about that. The first derivative test works only when my function is differentiable along an interval.